Thank you, Manuel, and thank you to the organizers for having me and also for organizing such a beautiful conference. I really learned a lot, and there's a multiplicity of perspectives, which is amazing here. And I am a little bit ashamed of speaking after serious scientists now, and I will just give you some kind of philosophical waffling. But nevertheless, since I'm the last speaker, you're kind of at my mercy. So what I'm going to talk about is a problem that has been presented by Ned Block. So the question I want to answer is this: are predictive coding models of perceptual information processing compatible with Ned Block's overflow hypothesis? Ned Block presented an argument some years ago, and this argument has gained a lot of prominence in the literature on consciousness and philosophy of consciousness. And I will introduce it in a second. Of course, before I can do that, I need to tell you what the overflow hypothesis is. Then I will tell you what the assumptions of predictive coding models of perception are. Then I will try to answer the question whether they're compatible. I will compare them. And then finally, I will consider some objections. So what's the phenomenal overflow hypothesis? Basically, throughout your waking life, you're looking at the world, you're engaging with the world, and you have this impression that everything in your visual field is represented with perfect acuity. You have an experience of rich perceptual flow. However, we know from a lot of studies that might not be so. So there's this tension in the literature, and Ned Block is one of the people who have discussed it first, between how the world seems to us and what we seem to learn from different perceptual paradigms about the limitations of our perceptual processing. So in his own words, the overflow hypothesis is the claim that perceptual consciousness is richer, that is, it has richer capacity, than cognitive access. When observing a complex scene, we are conscious of more than we can report or think about. So the idea here is that you take in a rich barrage of perceptual information, and then there's a cognitive bottleneck in the form of working memory, which limits how many items, how many perceptual objects you can hold in your working memory. And this has been strongly influenced by classic studies on iconic memory presented by Michael Spratling. I assume that most of you have heard about them, but just in case, if you can look at the cross, what have you seen? Well, I told you to look at the cross. So what have you seen? It was right, and yeah, 16 letters, 12 letters, a number of letters. And what's interesting and what Spratling found in 1960 is that in a free recall paradigm, which was something that we just here recreated, if I would ask you to enumerate these letters, you would all be adamant that you saw the whole grid. You had the experience of a grid of letters. But if I ask you to report what letters you saw, it would suddenly turn out that you can only reliably report about 4 or 5 of them. However, he found that in a controlled report paradigm, where he, after the stimulus offset, had an attentional cue that informed the participants which row they were supposed to recall letters from, it turned out that they were actually able to perfectly recall all the letters, right? So it's an interesting puzzle, because on one hand side, we all saw this. We all saw a grid of letters, and we had this perceptual experience of seeing the letters. On the other hand, something happens in our perceptual processing that prevents us from reporting all the letters that we supposedly experience. And here's just the data for how this changes with time. What I'm really interested in this talk, however, is the model that's underlying the perceptual overflow hypothesis. So according to Block, what explains your experience of the grid of letters in the Spratling experiment, even though you're unable to report it, is that you have a, oops, okay, there's a delay here. So you have an iconic memory storage register, and that iconic memory storage register uploads everything you see, basically. Everything you see in the visual flow is uploaded there for a very short duration of time, but it has very high capacity, this iconic memory storage. So everything there lasts in full richness for a very short time. Then there's consecutive stores of declining capacity, but increasing persistence. And so he said that phenomenal consciousness overflows access consciousness because you experience everything that's stored in the iconic memory store, but you can only consciously access, so cognitively process, the items that have been uploaded into the visual working memory store. So this is why he calls it an overflow, right? There's a mismatch between how much stuff is conscious in iconic memory and how much stuff you can actually process at one time in visual working memory. And this is a model of memory storage and processing, which is also quite old. So it's about as old as Sperling's original study. And I'll call it the phenomenal overflow model, right? That's the model that's underlying the phenomenal overflow. We can ask the question, what are its core assumptions? So I already told you about some of them, but just to make them very explicit, first of all, perception is bottom-up. Everything that you see is supposedly uploaded into iconic memory. Secondly, iconic memory, at least partially according to Block, depends on retinal persistence. So iconic memory is supposed to be something that happens super early, already on the level of the first neurons that communicate information from the retina. Thirdly, because as I just mentioned, it's a relatively old story about memory and perception dating back to the times when people only had digital computers with discrete memory registers and stuff like that. Memory limitations in processing are due to a decreasing number of discrete registers with predefined capacity. Basically, they thought that human memory works like a digital computer. And what follows from that is that when you have an item stored in one of the memory registers, attention is a faculty which uploads them into working memory, right? So what happens is basically if you see a face, attention is in the business of moving that item from memory register to memory register until it can get processed by other cognitive capacities. And what's important here and why I use this little emoji is that I wanted to illustrate to you this idea also here that it's really, you have an item in iconic memory and that item is preserved with full fidelity throughout the memory registers, kind of, right? Because if we go back to the Sperling stimulus of the grid of letters, you saw the whole grid of letters, right? Okay. So so you saw the whole grid of letters, and then the idea that how this explains the Sperling phenomenon is supposedly that you upload the whole grid of letters into iconic memory, where it just stays for a very short time. But if attention is skewed to particular registers, right, items from these registers are uploaded right away into working memory. Otherwise, if you're doing free recall, you're basically sampling this register at random, and at random, and what happens eventually is that the fidelity of the iconic memory or the kind of the items stored there evaporate. So those are the assumptions of the overflow model. And now I'm going to talk a little bit about predictive coding, even though I don't think there's much need perhaps with this audience, but just to be sure that we're on the same page. So I'm not talking about active inference and I'm not talking about free energy. I'm going back to old school predictive coding, which is a family of compression algorithms, basically, relying on the idea that the best way to predict incoming data is to acquire a generative model. So the original idea behind linear predictive coding was that if you have to predict the next step in a sequence of inputs, the best way to predict the next input is to take the inputs you already had and then kind of average them perhaps or do some kind of operation on them so that you can store a compressed representation of the regularities in the past inputs you received and then use that to try to generate the next input. And the reason why they are compression algorithms is because if you can estimate what the next input you're going to get is, then you can use this prediction to compare it to the current input, and then you just need to feed forward the difference, right? So you don't need to feed everything through. You don't need to feed the whole signal through the system. You can estimate what the future inputs will be, and based on that, you can only only process the difference. And that's important if you have a bottleneck. And indeed, we have many bottlenecks in our cognition, but perhaps the most famous bottleneck is on the retina. So this is where predictive coding was first applied. It was later applied to Rao and Ballard to perception in the form of a neural network. And from there, you know how it went, right? So now it explains everything, supposedly. But I'm just gonna stay with neural networks and perception. And so the reason why there's a bottleneck on the retina, just very briefly, is that basically you have ganglion cells depicted there on top, and these and many other cells. But the thing is that something happens on the retina, which is that the number of ganglion cells is way smaller than the number of photoreceptors. So depending on where you are in the retina, the ganglion cells will receive inputs from up to 100 photoreceptive cells. So between 10 and 100, depending if you're in the fovea or in the peripheral vision area. So what that means is that ganglion cells must code information in a way that is not only compresses a lot of information that they're getting, possibly from up to 100 cells, but what that also means is that they need to code information dynamically. And the most recent application of predictive coding to the retina by Hosoya and colleagues from Riken, actually from 2005, they have shown that indeed the ganglion cells are not only compressing information, but they're coding information dynamically, which means that what information ganglion cells are receptive to depends on the, for example, scene statistics of the image. So basically, if you see an image with a lot of vertical lines, it will turn out that ganglionic cells more often than not fire when, did I say vertical or horizontal? Vertical. So they will more often fire for horizontal cells, right? For horizontal lines. So that means that they're kind of trying to predictively code for the unexpected input. And what's also interesting, and what's part of the motivation behind this talk and this paper, is that there's barely any mention of memory in the predictive coding literature. So these people don't think about memory storage and stuff like that. They think about, flows and actions and coding. There are a few papers now, but still a lot of this stuff hasn't been touched in that literature. So very briefly, predictive coding assumes that there's a neural network that approximates inputs composed of two populations, and that there's a neural network that approximates inputs, and it's composed of two populations of neurons. And basically what this network is supposedly doing is it takes some input vector and it tries to approximate it with a reconstruction vector, which is created on the basis of some stored latent variables in a weight matrix. And the two populations of neurons are error units, which receive the signal values and combine them to output the residual error, and prediction neurons, which update the latent variables by performing gradient descent on that error, right? There's more stuff, of course, and there are many predictive coding algorithms. As I said before, it's a family of algorithms. So there are many different ways to do predictive coding, and I'll get back to that towards the end of the talk. But the main story is more or less the same, that if you're implementing it into a network, you get something like that. And the main idea that was kind of gained prominence in the literature and why predictive coding as a theory of cortical responses gains popularity is because people figured out, oh, well, you can take that kind of network and then you can layer them up in like a deep neural network, right? And so this is what I will call the predictive coding model. And I'm going to operate with some kind of metaphorical description of it, just to make it easy and so you can see how it aligns with the other view. So according to that model, perception is supposedly top-down, right? Because the most important thing is the reconstruction of the signal. You're reconstructing the signal. That's what the network is supposedly doing. And then it's comparing that signal to what's actually what the actual input is, and then it's only propagating errors. So only the difference between the actual input and the reconstruction is supposedly passed forward. Compression, because of this, is lossy, because if you have a signal and you're removing the predictable component of that signal and only passing on the difference to the next network, that means that that next network doesn't know what the original signal was. It only knows what it gets from below, right? So in principle, it might be impossible to reconstruct the original signal based purely on that. Thank you. On the error signals alone. And then I didn't mention that in the equations, but there's also this idea that attention is implemented by a biased competition and is present throughout the perceptual hierarchy, and that attention basically is in the job of biasing the error connections between the layers of the deep neural network. And I should also say that it's also usually assumed that these layers process features which are of increasing abstraction as we move away from the sensory periphery. So just to give you a kind of a caricature of what perception is supposedly looking like when we think of these models and implement them as models of perceptual cortex, for example, if there's a face, just like before, what supposedly happens is that because something changed in your environment, there's an onrush of prediction error, and it's compatible with neurological data, which shows us that the first forward sweep in perceptual processing is actually unconscious, and then slowly there's the refinement of what it might be out there, and different layers are usually, as I said before, computing different features of the inputs, and finally at some point the network settles into an object, right? A stable representation of the object at the last processing stage, and that informs everything else, something like that. And so in this isn't the main reason why in that literature the catchphrase that no one remembers now where it originated, but the catchphrase is perception is controlled hallucination, right? Because basically you're reconstructing the input and you are anchored to the world via the error signals, but the error signals, the feed-forward error signals are not the whole input. You're not kind of getting things from the retina and just processing them one after another, but rather you're kind of guessing what's out there based on limited data. So what's the comparison between these models? Well, the question, just to remind you, was whether predictive coding models of perceptual information processing are compatible with Ned Block's overflow hypothesis, and here's a little comparison. So when it comes to perceptual content, according to the overflow model, the perceptual content is processed in a bottom-up fashion. According to predictive coding model, it's actually the top-down generation of the reconstruction of the original input signal that's key. When it comes to retinal coding, overflow model assumes that it's static, that it's like something to do with memory registers, right? Remember that I said that the iconic memory store is dependent at least partially by what's happening in the retina, and because it's assumed to be discrete, therefore overflow model assumes that retinal coding is somehow static. Predictive coding models, on the other hand, assume that it's dynamic, that what the retina codes is informed by top-down expectations and lateral connections. Memory is discrete and pre-limited, as I said before. Predictive coding models don't really say much about that, and I didn't have the time to get into the details of that, but there's some evidence that shows that depending on the stimulus structure, people are actually able to store different numbers of items in their memory. So there seems to be a case that memory is more dynamically coded, just like the retinal coding is. In terms of bandwidth and fidelity, on the overflow model, it's high because everything that gets uploaded into iconic memory store is uploaded there with high fidelity and then just moved around. On the predictive coding model, on the other hand, the bandwidth is low. That's the whole reason for postulating predictive coding on the retina and further up, is because there are communication bottlenecks. And finally, when it comes to attention, on the overflow model, attention is a localized cognitive faculty, whereas on the predictive coding model, it's something that's distributed across the perceptual hierarchy. So in short, are predictive coding models of perceptual information processing compatible with Ned Block's overflow hypothesis? Doesn't seem like it. But there are some possible objections that I will try to just quickly go through. So objection number one would be that this is a caricature, of course. This is just a story about the construction of visual percepts. It doesn't say anything about the limitations of cognitive processing. So I didn't say anything about Block's assumption that, or claim that access consciousness is limited in the number of things that can be processed cognitively. And indeed, this is a problem for predictive coding, I agree. And this is kind of a challenge for predictive coding models, right? Predictive coding models should actually account for what we know about the limitations, even if they are more soft than hard on memory processing. But what I would say to this objection is that the main point here is that predictive coding compression is lossy. If the expected components of the sensory signal are removed, they cannot be recovered at a later stage. And what that means is that you cannot have any kind of overflow because there's nothing that's being preserved from the beginning. In fact, there's nothing to be preserved almost. That's one thing. And then if I would say that, I expect another objection will come up from people who know their predictive coding algorithms, which is that not every predictive coding algorithm, despite what Andy Clark, Carl Friston, and Jakob Hulby have told you, not every predictive coding algorithm processes errors in a bottom-up fashion. So in fact, Michael Spratling has proposed something that's what's called a predictive coding biased input modulation via predictive coding biased competition via this divisive input modulation algorithm. A kind of a very, no wonder no one is talking about that, but a mouthful. But his algorithms are actually very good, and his models are very good. And in these models, reconstructions are still processed in a top-down manner. However, what's happening is that the bottom-up inputs are actually the predicted values of the latent variables. In technical terms, he describes them as the most likely coefficient. And so the reason why this is possible is because on his model, there's a different mapping of these layers of error units and prediction units onto cortical hierarchies. So on the left-hand side, you can see that's taken from his paper from 2017. Rao and Ballard's original cortical predictive coding model assumes one mapping onto cortical regions, and Spratling's assumes a different one. And that's where the difference comes from. It should be noted, however, that the predictive coding biased competition divisive input modulation algorithm has not been extended to the retina. So everything I said about the retina is still applicable there. And the second problem is that I can grant you that even though perception cannot be said to be exclusively bottom-up under Spratling's algorithm, all the other dissimilarities still hold because he also assumes that attention will be implemented via biased competition and so on. Okay, so conclusion. Predictive coding models of visual processing are incompatible with at least some of the assumptions behind the overflow hypothesis. However, I would say that this is a kind of a constructive point for predictive coding in the cortex. Some of the empirical findings that motivate the overflow hypothesis, for example, working memory limitations, need to be addressed by future predictive coding models if predictive coding modelers want to claim that they have the best perceptual processing model in town. And with this, I will thank you. That's my email, and that's the website of the research group in which I am currently employed. And these people give me money for this. Thank you so much.
Time for questions.
Thank you so much for the great talk. I have a question for, so in the visual attention literature, the overflow hypothesis often contrasted with the gatekeeping hypothesis, right, which says that you don't have deep consciousness without attention. So do you think predictive coding framework as support a kind of gatekeeping hypothesis, or do you think that it's like it dissolves the problem?
Okay, so that's a very good question. Thank you. I actually haven't thought that much about gatekeeping hypothesis. So this is still work in progress. I should have said that at the beginning. But so I think that the view that this is most compatible with actually is the generic phenomenology hypothesis. So this idea that in the Sperling experiment, so this is Michael Cohen, who's been mostly kind of pushing it forward on the empirical side, and The name generic phenomenology has been coined by Rick Grush many years ago. And so their idea is that basically when you see the grid of letters in the Spratling experiment, you form a representation which is somewhat categorical of what you saw, but that what you don't realize is actually there's no detail there. So you know you saw letters, but that experience was devoid of detail. And so what happens later on is that kind of by cueing attention to particular memory traces or kind of decaying traces of neural activations, you can kind of upregulate certain bottom-up signals, and that kind of refines the hypothesis top-down reconstruction of what you saw. About the gatekeeping, I think I would say that it probably dissolves it, but it's as much as an advantage as a problem for these models, because on one hand side, they are based on biased competition, and biased competition is well documented in empirical literature, and it's good that they maybe dissolve the gatekeeping problem. On the other hand, there is an issue there where suddenly everything becomes attention in a way, right? Because attention is everywhere, and so suddenly it becomes you lose a grip on what psychologists usually call attention, because it seems to be something that's just happening all across the brain, and that's maybe a little bit of a problem.
Yeah, okay. Thank you for the talk. That's great. I just had a question about the sort of the idea that the lossiness of the predictive coding hierarchical sort of situation might. Oh, sorry. Yeah. So this lossiness, I guess my question is, if they're being totally agnostic about theories of consciousness, but let's say there's one where the perceptual experience might arise from some process that's happening at a lower part of the hierarchy that causes some component of phenomenology. And then there's like this higher level at the very end where you have access. And yeah, I don't understand like exactly why that is ruled out. Like, so because if you're supposing that the access at the very top level is what needs to be explained, then yes, the lossy thing poses a problem for overflow. But that seems to be presupposing that access consciousness is what counts, where maybe what Ned is saying is that there's like more to it than that. So can you just speak to that problem? I don't know if I was clear. I didn't try to clarify.
Do you want to maybe rephrase it in a one sentence? I know this is like turning the tables on you, but so the point is that according to Block, it's not all about access. And here, whether, the idea that access maybe doesn't matter that much for perceptual experience wouldn't also be the case. Something like that?
Yeah, something like that.
Okay, so the problem I think here would be that I think that predictive, so this whole thing started many years ago and then I abandoned it and now I got back to it because I think that actually these models dissolve the distinction between phenomenal and access consciousness. And the reason for that mainly is that according to Block, access has something to do with attention, right? It's attention, like working memory and attention, that's basically where access happens, according to him. And if you have attention everywhere, basically, throughout perceptual processing, then it seems that, in principle, a lot of stuff is accessible to you, right? Like that access is kind of distributed. So access and phenomenology always go together in a way in these models. And so you might think at first that this is very implausible, right? Because there's, for example, all these phenomena of unconscious perception. The interesting thing about the literature these days about unconscious perception is that the number of phenomena that we can actually induce unconsciously is shrinking dramatically, because as we're developing better and better measures of whether people were aware of the stimulus, it turns out that you can actually do less and less with unconscious processing. So it does seem a little bit like it is at least maybe plausible that actually, access and phenomenology kind of always go hand in hand, despite what Block claims.
Yeah, okay, that does answer my question. Thank you.
All right. At least a few more questions that I've seen some raised hands already, but I guess this is around the time we are supposed to end the last session of this amazing workshop. So I'll thank our speaker one last time.